Hello. In this video, we are going to continue on with this business of calculating the canonical partition functions for model Hamiltonians. If you remember from previous videos, we have introduced the canonical partition function and explained how it can be calculated using the equations shown on this slide. Furthermore, we have seen how once we have the partition function, the equation of states and formulas for the average energy can be calculated by taking appropriate partial derivatives of the logarithm of the partition function. When dealing with model systems, we have seen that there are two important things to think about. First of all, we need to know the Hamiltonian for the model system, as this is the h that enters our equation for the partition function. The Hamiltonian is an expression that we can use to determine the energy of a microstate. For clarity, I have always shown the Hamiltonian in blue in the examples I have done thus far. The other component we need to think about when calculating the partition function for a model system is the way the sum, or integral, over microstates is performed. This part I have shown in red in the expression here that I have for the partition function. Ultimately though, if we know the Hamiltonian and we know how to sum over microstates, writing out an expression for the partition function is not particularly difficult. It is difficult, and often impossible, to simplify the Hamiltonian into some more mathematically malleable form. But by now you hopefully understand what the partition function is and how it can be calculated. On that assumption, then, let's continue on with what we are going to cover today. In previous videos, we have introduced the following useful way of classifying model systems. In the videos on lattice gases and the Ising model, we have looked at how to model systems in which the particles sit on a lattice, and have learnt that how we can do so when these particles are not interacting, the case of the lattice gas, and when they are interacting, the case of the Ising model. In those two videos, we also alluded to model systems in which the constituent particles are not sat on a lattice, sites. In these systems, the constituent particles are free to move about, rather like the atoms in a gas. It is one of these non-lattice systems that will be the subject of this video. We are, in fact, going to look at a system of non-interacting particles that are not sat on lattice sites. This system is known as an ideal, or sometimes perfect, gas. Here is a schematic diagram of a particular microstate of an ideal gas. Each of the circles represents an atom. You will notice that each of the atoms takes random position and there is no regular repeating pattern arrangement of particles. That is to say, there is no lattice. There are n of these atoms in total, and these atoms are confined in the volume V. They might be confined in this volume because the gas is in some container or other. As I have already explained, there is no interaction between the particles, so the energy of the system does not change as atoms are brought closer together or as atoms are moved further apart. Each particle is moving, however, and as such, each of these moving particles has some kinetic energy. Now we know how to calculate kinetic energy. It is just 1/2 mv squared, or p squared over 2m, a formula which by this stage is an old friend of yours. The Hamiltonian for this system is thus given by the expression shown here, which is admittedly a bit more complicated than p squared over 2m, but that complexity just reflects that each atom will have a momentum in the x, y, and z directions, and we have to do p squared over 2m for each of these three components of the momentum. Easy enough, I hope. Right. So having worked out what the Hamiltonian for this system is, let's see if we can work out how to do the other component of calculating the partition function, namely the sum over microstates. Well, actually, before we do this, let's just make our life a bit easier by recalling something that we learnt when we looked at the lattice gas. If you remember in that video, we found that when we manipulated the partition function, we got to a product of summations like the one shown here. We could write this product of summations because there were no interactions between the particles the system was composed of. Furthermore, we quickly realized that all these summations were the same, and that as such the partition function for this n-particle system was simply the partition function for a system composed of one atom raised to the power n. Now we know that the atoms in our ideal gas do not interact, so we are going to try to see if we can't adopt a similar strategy in this video. We will start by calculating the partition function for a system containing only one atom. We are then going to use a trick, like the one above, to get the multi-atom partition function. Interestingly, we will see that the trick is not identical to the one above, but we will come to that in due course. Right, so what microstates can a system containing only one atom bind itself in? Well, first, the particle can be in any position in the box, so we are going to have to sum over all these various possible positions that the atom could be in. Then, on top of this, the particle will be travelling in any direction very slowly, or very quickly. So we are going to have to consider all the possible speeds and directions the particle might be travelling in. There is a complexity here though, as both these quantities, the positions of our particles and the momentums of our particles, are constant, continuous quantities. We thus cannot calculate the partition function by performing a summation like the one shown here. As these are continuous quantities, we are going to have to instead go to the continuum limit and calculate an integral. Now, if you remember, a single integral is the area under a curve, as shown here. Thus, when we take an integral of a function of two or more coordinates, we must always explain what line we are travelling along. How then do we express this process of summing over all microstates as an integral over coordinates? The answer to this question comes when we remember how surface integrals are performed by performing multiple integrals. To calculate the partition function, we simply integrate over all the coordinates as shown here. Furthermore, this is not even necessarily that surprising. After all, when we calculated partition functions for the lattice gas in the Ising model, we summed over all the coordinates that defined our microstates. All we have done here is replace the sums by integrals. In fact, if you look at the scientific literature on statistical mechanics, you will see that people who regularly work in statistical mechanics use the integral and summation sign rather interchangeably when talking about the calculation of partition functions. This would probably upset pure mathematicians, but in physics it's just fine. Right, so having established that we calculate the partition function by calculating this definite integral, let's have a look at the limits of the integration. I have assumed that my gas atom is confined in a cubic box with sides of length L. And I have set L equal to the cube root of V so that the volume of the box is V. The x, y and z positions of my single atom can thus take any values between 0 and L. That is to say, the atom can be anywhere in the box. As I stated on the previous slide, the momentum can take any value. The atoms can be travelling very fast, or they can be travelling very slowly, and they can be travelling to the left or the right. The integrals over the momentum coordinates thus all run from -infinity to +infinity. Let's now do this integral. The first part of this integral is easy. Each of these integrals over position coordinates is an integral of a constant, as nothing in the integrand depends on x, y, or z. Each of these definite integrals will thus give us an L. As we are taking the products of these definite integrals and L cubed, we will get L cubed, which is just V. This second integral looks more tricky, but is made more straightforward once we realize that we once again have the exponential of a sum. We can rewrite this exponential of a sum as a product of three exponentials, which makes it possible to separate the three integration variables as shown here. Notice that these three integrals are the same. We can thus write this product of three definite integrals as a cube of the following definite integral. The integrand inside this integral is a Gaussian. So this integral is a well-known Gaussian integral, which you probably learned to solve in the first year of your degree. We don't need to remember how precisely we solved it back then, though, as we can look up the integral in tables. If we were to do so, we would find its solution written something like this. Once we recognise that a, in our case, is just 1 over beta over n, we can quickly work out that the value of the integral shown is just the square root of 2 pi m over beta. When this is cubed and multiplied by v over h cubed, we thus find that the canonical partition function for a system containing one gas atom in a box with volume V is given by the expression shown at the bottom of this slide. Now, hopefully, the eagle-eyed amongst you are all asking a question about everything that we have done thus far. Namely, what the hell is h in all of this? For those amongst you who are thinking that h is obviously Planck's constant, but wondering where in the hell that came from, then really well done. H is indeed Planck's constant, and it appears here for reasons that are deeply rooted in the way that statistical mechanics is applied on quantum systems. Statistical mechanics was, however, developed before the advent of quantum mechanics, and even some of the earliest proponents of statistical mechanics acknowledged that some constant must appear in these integrals for the following reasons. If you think about what we do with partition functions, we regularly take logarithms of these quantities in order to calculate free energies and such. In order to take the logarithm of a quantity, however, that quantity must be unitless. In other words, z cannot have a unit. If we calculate z by taking the following integral, it will have a unit, however. Each of the first three integrals over length will contribute a unit of length to the final partition function, and each of the second three integrals will contribute a unit of momentum. The partition function, the integral shown here, will thus have a unit of length cubed multiplied by momentum cubed. We must therefore divide by a constant with units of length cubed multiplied by momentum cubed in order to prevent the integral from having any units and in order to ensure that z is a unitless number which we can take logarithms of. It turns out that Planck's constant cubed has the appropriate unit, although this is not the reason that we use it. If we argue in this classical and not quantum way, we can use any constant cube with the appropriate unit of length times momentum in place of h here. Having cleared up what h is, then let's return to the result that we had just derived for the partition function for one atom, which is shown again at the top of this slide. If you remember, we said that we wanted to calculate from this one atom partition function the partition function for a system of n non-interacting atoms. We had also noted in an earlier slide that when we were looking at systems on a lattice, we had done things like this. We'd calculated the n-atom partition function from the one-atom partition function by simply calculating the nth power of the one-atom partition function. Furthermore, we could even justify this course of action based on the derivation we had performed for the n-atom partition function. The relevant part of this derivation is shown again at the bottom of this slide. We might therefore suppose that the canonical partition function for a system of n non-interacting gas particles is given by the expression shown here. Let's investigate this a bit further by trying to calculate the free energy of the gas. If you remember, we can calculate the free energy once we have the partition function using the expression shown here. When we stick the expression that we have just derived, we get the following result for the free energy of an ideal gas, which we can further simplify by remembering that the logarithm of a product can be written as a sum of logarithms. We even see what would have happened had we used some value other than Planck's constant in order to get rid of the units of the integral when calculating z. All the terms in the second of the two integrals here are a constant, so we can combine them all into a single constant with units of 1 over volume. The expression for the free energy that we have here is thus the difference in the free energy for a system with volume V and the free energy of some reference state. If we change h to some other constant, we simply change the value of the free energy in this reference state. Let's use this expression for the free energy that we've just arrived at to now perform a little thought experiment. Let's suppose that we have some atoms in a volume like this, and let's suppose that we think about trying to calculate the free energy of the system by imagining that this volume is divided into two chambers by this imaginary red dashed line. In the leftmost chamber, there are N1 atoms in a volume V1, and the formula that we have just arrived at tells us that these atoms have a free energy which is given by the expression shown here. Meanwhile, in the right-hand chamber, there are N2 atoms confined in a volume of V2. These atoms have a free energy given by the expression shown here. The division we have introduced here is imaginary, however. What we have in actuality is N1 plus N2 atoms in a volume V1 plus V2. The free energy of this system should therefore be given by the expression shown here. Furthermore, the difference between what I've called F1 and F2 and F1 plus 2 should be equal to 0, as the division we introduced was imaginary. In other words, the manner in which we calculate the free energy of the system, whether we do it by considering subsets of atoms in partitions of the volumes and adding these together, or whether we simply calculate the free energy of all the atoms at one time, should be irrelevant. If we take F1 plus 2 and we subtract F1 and F2 from this, we get the following, however. Furthermore, V1 plus V2 over V1 and V1 plus V2 over V2 are both greater than 1. The difference, shown here, is thus less than 0, which is a disaster as the free energy is supposed to be a function of state. The value of the free energy should thus not depend on the manner in which the state was prepared. This particular disaster is known as the Gibbs paradox, and the resolution is not straightforward. In fact, the resolution to this problem is still being actively researched and is deeply rooted in quantum mechanics. Having said that, a simple resolution comes once you realize that a part of the problem is due to the fact that the atoms are indistinguishable because they do not sit on a lattice. As such, it does not matter what scheme we use to label the atoms. If we swap the labels on atoms 1 and atoms 2, the microstate we are in does not change. However, when we calculated the partition function by taking the integrals, we assumed that these two microstates were distinct. To resolve this problem, we just need to remove this multiple counting. In other words, we need to divide the partition function by a factor of n factorial in order to remove microstates that differ only by the ordering of the labeling of the atoms. The final partition function is thus given by this expression. Let's now show that introducing this factor of n factorial to the partition function does indeed resolve the Gibbs paradox with the free energy that we just showed. To do this, we are going to need to note that when we calculate the free energy from this revised partition function, you get the following. At this stage, it is also going to be useful to remember a result known as Stirling's approximation, which tells us that for large n, the logarithm of n factorial is approximately equal to n log n minus n. When this approximation is inserted into our expression for the free energy, we get to the following. Now remember the expression that we got for the change in free energy when we added the imaginary partition between the two chambers. This expression is shown again here. It is easy to show, I will leave it to you as an exercise, that when we use the expression for the free energy shown on this slide, in place of our old expression, the expression that did not include the factor of 1 over n factorial, this equation becomes as follows. Now in this expression, n1 over v1 and n2 over v2 are equal to the number density of the gas. Furthermore, v1 plus v2 over n1 plus n2 is just 1 over the number density of the gas. Now, because we did not in introducing the partition function, change the number of atoms in the system or the volume, we did not change the number density. As a consequence, the rows in the numerators and denominators here cancel, and we are left with the logarithm of 1, which we know is just 0. We thus have the desired result, namely adding or removing the partition does not affect the value of the free energy. The free energy is thus, once more, an equation of state that does not depend on the manner in which the gas was prepared. The last thing we are going to do in this video is calculate the equation of state for the ideal gas. To simplify matters, we are going to write out our expression for the free energy as shown here, and combine all the constants in the second exponential, in the last term of the equation at the top, into a single number v0. The c, meanwhile, is going to equal the logarithm of n factorial, which we can calculate directly or using Stirling's approximation. To get the equation of state, we need to remember that the pressure is equal to minus the derivative of the free energy with respect to the volume. When we insert this expression for the free energy, we find that the second two terms here are equal to 0, as the derivative of these constants, the derivative of a constant is 0. The derivative of the logarithm of v with respect to v is just 1 over v. So we are thus left with P is equal to n kBt over v. In other words, what we have is the equation of state for an ideal gas, PV equals n kBt, an equation that we encountered in the context of classical thermodynamics. What we have seen now, though, is that this equation of state drops out naturally if we consider the statistical mechanical treatment of a model system of non-interacting gas atoms that are not sat on a lattice. Pretty cool, huh? So to summarize, we have in this video considered a system of non-interacting particles that are not sat on lattice sites, and have shown that the partition function for such a system is given by the expression shown here. We then showed, by taking the appropriate partial derivatives of the logarithm of the partition function, that the equation of state for this particular model system was the equation of state for the ideal gas that we encountered in classical thermodynamics, and that was first determined by experiments that were performed in the 17th century. On this happy result, I will finish and thank you for your attention.